Particularly related to earthquake resistant design, I'll be talking about ductile detailing for moment resisting frames, and if time permits, we'll also talk about buckling resistant braces. I'll go through the concept of buckling resistant braces. It's not a very new concept, but it's new for us in India. Some of the construction projects have started using buckling resistant braces. I'll start with some images of Bhuj. Bhuj earthquake is going to complete 25 years on 26 January next year. And these are some images. I will not talk about these images. They are self-explanatory. Just to give us a reminder what happened 25 years ago and what we are up against, the nature, the force of nature that creates such disasters. So coming to the topic at hand, we'll just go quickly through the performance of steel moment resisting frame buildings in past earthquakes. The very defining moment earthquake for moment resisting frame was the Northridge earthquake, which happened in 1994, January 17, 1994, very shallow earthquake. It had damaged buildings which were more than 100 numbers. That was at the time of the earthquake, they had identified that 100 buildings were damaged. Very few buildings, steel buildings, moment resisting frame buildings collapsed because of this earthquake. That was a good thing, but the performance was not as expected. All these buildings that were subjected to the earthquake, the Northridge earthquake, were built during and before 1980s. They were 6 stories or less, medium rise or low rise structures in today's terms, but at that point in time they were called medium rise building. A few taller buildings were also there, but all of them were designed using the philosophy of moment resisting frame. Moment resisting frame in a nutshell is when you have a frame, at the beam column joint there's a moment transfer. There is no brace available to transfer the force diagonally. Whatever force is coming from top laterally, all the direction force is transferred to moment transfer at the beam to column joint. And they were built using the prescriptive moment connection. Beyond the earthquake, after the earthquake, they realized that most of the behavior was not as expected. So they started investigating. NIST is National Institute of Standards and Technology in the US. They examined about 12,000 steel moment resisting frame buildings. And these are the numbers that we are talking about. 1,200 floor frames and 5,000 beam to column connections were examined. This was almost a 3-year long study, and more than 100 strong special moment resisting buildings were found to be damaged. Special is a term used to describe the way the detailing is done. And as the name says, special is supposed to be better in earthquake than an ordinary or an intermediate frame. All these buildings that they were found to be damaged were designed as per the stringent detailing requirement of a prescriptive moment connection. I'll show you what the prescriptive moment connection is, where the connection design, the specifications, and the proportioning of the connection was specified by the code, which is rarely done in today's day and age. There are very few prescriptive connections which are given. Indian codes don't do that. Only in this code, the Uniform Building Code at that point in time it was called, they had a prescriptive moment connection and they were supposed to behave well. So what happened, these are the problems that happened in the moment. This is one of the photos of a beam to column connection. This is a column, this is the continuity plate, these are the flanges of the column, and this is the top flange of the beam, one of the flange of the beam, where you can see that it's completely sheared off during the earthquake. So the problems that were tearing of weld, minor cracking, divot pull out, basically if you see this picture here, the flange where it is connected to the flange of the bottom flange of the beam where it's connected to the beam flange gets pulled out. This, if you can see, is a welded area which gets affected during welded because of the heat that is supplied. It's called a heat affected zone, which changes the chemical and the physical properties of the steel which is there. And there were column web cracking similar to this, beam flange cracking, there were cracks in the beam flange, and shear tab cracking. Shear tab is the shear connector which connects the web of the beam to the face of the column. So in this also there were shear tabs. This, when you look at it now, they seem like obvious points of failure, but because they were done as a moment resisting frame or the prescriptive moment connections, they were supposed to behave in a ductile manner, which in this earthquake it was shown that they were not so. Though the problems that we saw was, this is a beam to column connection. So how they are connected is, this is the bottom flange of the beam, this is the flange of the column from here, this is a zoomed part. They would, this would be a complete joint penetration weld. It's a butt weld. we call in Indian terminology or the Indian codes, they call it a butt weld. Basically, the flange is not touching the column. You have a backup bar. It's just a small bar. It's like a shuttering, which we put in concrete. It's a shuttering for the weld to be deposited here. It is tack welded to the column, and the weld is deposited for this thickness. These thicknesses could be in the range of 60 to 70, 80 mm thick. So the weld is deposited layer by layer so that the weld doesn't spill down. This is put in place. Unfortunately, these backup bars were left in place after the construction was done, because you move on to the next one, and having a backup bar at that point in time didn't seem like a problematic thing. But then later investigation showed that this unfused interface actually was a crack that we had already installed or put in place in the structure. The other problem was top and bottom flange. Top flange, like composite constructions, most of the constructions were composite construction. Top flange was embedded in the slab, concrete or any other material. The bottom flange was free. So naturally the stresses that were there at the top flange were reduced because most of the stress was shared by the concrete also. And the bottom flange was subjected to a larger stress. And that's one of the reasons where the damages were more concentrated in the bottom flange. One picture I'm showing here, this is the top flange, this is the web tab, and this is the beam, this is the face of the column, that is where that crack happened. I'm going to go a little faster on this. So prescriptive moment connection, what was the problem? They were supposed to be welded or bolted to the joint was supposed to be welded or bolted, where the flange is welded to the flange of the beam is welded to the flange of the column, and they were expected to have good ductile behavior. When ductile behavior, I mean there would be some kind of plastic hinging or inelastic action focused somewhere in the structure, which allows you to dissipate the input energy of the earthquake. And they were supposed to develop full MP of the beam. MP is one property of the beam where you take the section and multiply it by certain numbers to get that moment. So once you develop the full MP of the beam, that is the full capacity of the beam. That was seen to be not happening. This was the prescriptive moment connection that happened, like I showed you earlier. Web tab, shear tab, fillet welds, continuity plate to strengthen the column, backup bar, top and bottom complete joint penetration weld. This was a very simple connection, very easy to implement. The numbers of the sizes of this connection, the bolts, all this was prescribed in the prescriptive connection, or there were methods to calculate these numbers. So what we saw, this was based on a few studies before the earthquake. These are the studies that I have listed, and the study emphasized on importance of welding. As time went by, people started optimizing the quality of weld, making low cost electrodes, and that actually resulted in poor welding which was available for the previous buildings. Only thing that happened, based on these 4 or 5 studies, they had actually developed this connection. These were lab studies. Some institute had done that. None of these buildings were ever subjected to real earthquakes. Northridge earthquake was the first earthquake that tested them. And it was used widespread. Again, these are the same damages that I'm showing here. So similar damages here. Top floor embedded and reinforced by the concrete, and the bottom flange had most of the damage, and this was widespread and everybody had noticed this. So this was a few weeks after, 5 weeks after the Northridge earthquake. I'll read this. In the past earthquakes, unreinforced brick and stiffly designed concrete buildings were considered to be most vulnerable to collapse against steel buildings which were supposed to be ductile. Even when we talk to non-civil engineers or non-structural engineer, they always have a feeling that steel is a ductile material, concrete is a rigid material or brittle material, brick is a brittle material. But this was proven by this earthquake that it was not so. The buildings made of steel were deemed to be safer because they tend to bend but not break. Basically the process or the phenomenon of ductility. But during the earthquake, it was proven that this was not true. Although the buildings did not collapse, they were seriously weakened because the moment action was disrupted because of the damage that occurred in the buildings. One building that had this damage was a 6-story American insurance consultants building. All the damages were all focused in the moment frames. The joints, basically beam to column connections. Exactly 1 year after, Northridge occurred January 17, 1994. 1 year after that, the Kobe earthquake struck. This affected about 1 lakh building, 100,000 buildings, and 15,000 were lightly damaged, but there was extensive damage to steel. Japan was known to be pioneer in producing good steel, and they had put to use through the 60s, 70s, 80s, they had constructed a lot of steel buildings, and this had caused collapse of a few steel structures. These are some of the pictures of Kobe earthquake. This is a total shearing of the column at the bottom flange of the beam, tearing of the shear tab, extension. The complete weld which is there here was totally torn off, and this is the box column. Similar damages at the foundation of the column because of the pounding effect, because it's a moment frame. When the building tries to do lateral swinging, the columns are pulled up and down, and basically because of the pounding, the bolts were also pulled out. These bolts are pulled out and the concrete pedestal collapsed. Another building here, this was a building between two masonry buildings. This is a masonry building, this is a masonry building. Old masonry buildings, Japan, about 100 years old building. This was a steel building constructed between them two. Nothing happened to this building, very rigid building. It's exactly contrary to what LA Times reported. They are supposed to be rigid and not bend, but because of the way, there was supposed to be a horizontal girder here at all the levels, which was weakly welded to the column. So in the first jolt of the earthquake, that welded thing came off and the entire thing collapsed. Nothing happened to these buildings. In fact, they continued using this building beyond the earthquake. There was another earthquake that happened which defined, which is used to define the development of steel construction. This was a Mexico City earthquake. The uniqueness of this Mexico City earthquake, Mexico City is sitting on a bowl of, it's a lake actually, filled up with clay, and it has a very long, when buildings are constructed and when the earthquake comes, they give long period earthquakes. They are not like the earthquakes that we experience in India near the Himalayas, nor like Northridge earthquake, nor the Kobe earthquake. It's a slightly different earthquake. Here also some of the buildings were damaged. This is one more thing I want to show you. This is not earthquake related damage. This is Elliott Lake Algo Center Mall collapse. Not because of the earthquake. This was collapsed because of the deficient design and the lack of maintenance of the building. So this was around 2012, built up area and all that. It was constructed using steel as a main frame. On top of it, there were precast pre-stressed slabs of about 9 meters span with a concrete topping. It's a standard precast system that is connected. The failure was in the beam to column connection. That's why I'm trying to show you this here. How can a precast building, not because of the precast, be collapsed or have a problem in? There were leakage from the hollow core slabs. I'll show you the pictures here. This is a detailed sketch of the report after the investigation. This is the hollow core slabs here. There's a beam in this direction, there's a beam in this direction. And there's a joint, always the hollow core slabs are always sitting on top of the beam. There has to be a support there. So the topping that was put on top, about 75 mm to 100 mm, cracked because of the deflection of the beam. And that led to ingress of water and led to corrosion. And most of this, because it was a mall, lot of false ceiling was there and it was not noticed and it suddenly collapsed on 23rd June. Similar, the other beam is that same problem. The water comes through the joint and passes on top of the flange of the and spreads in all the directions. Now, just to say why steel, this is, you are very familiar with this. This, I will not explain this, I'll just show the graphics. Basically, that is the stress strain behavior of steel, right from elastic to rupture. Steel has a very unique behavior unlike any other material, concrete or brick or timber. These are the regular construction materials that we use. It has a horizontal plateau at yield point. It's an important feature of steel because that's the part that gives us ductility, very large ductility. At the same force level, it just gives a lot of deformation without collapsing. There's no rupture. The rupture happens much later. This is about 300% elongation. This is about 15% elongation. This is about 0.1% elongation. The yield happens at 0.1%. So this is one property of steel that is very effectively or can be very effectively used for resisting lateral loads in earthquake. So it's a material which is ductile, used to make ductile structures. I've just put together I'll go through this. These are some, when I share this, you can look at this. These are the items which are for steel. On the left column are the items against concrete. Only one item which is for concrete is the natural fire resistance, because we use concrete for fire resistance. But steel is not naturally fire resistant. We have to take a little more effort to make it fire resistant. But the rest of the properties, basically strength, quality control, earthquake resistant, cost and construction timeline, all are basically working in favor of steel. That's why steel is supposed to be a preferred material of construction. So if you look at the moment, talking about moment resisting frame, there are different types of connection. I've listed them here. These can be broadly categorized as weak or soft connection, flexible connection, semi-rigid connection, rigid connection, based on the stiffness that happens, which is the moment versus the rotation. You take a beam column and apply a load on the beam, the joint will rotate, and how much it rotates, based on that you define this. Even our code defines it in a similar fashion where we say semi-rigid and rigid connections. This is the basis, and these are the connection types that fall into the different categories. So what is the desired behavior of a moment connection? Basically, if you see this as plastic moment and the desired ductility in the frame, if it is less than the expected strength, it's partial strength. If it is more than the plastic capacity of the beam, it's full strength. If the desired ductility or the deformation is less than the desired ductility, it is brittle. If it is more, it is ductile. So these are the 4 quadrants that we normally put all the connections in. And if you look at the moment to rotation behavior, if you have this connection, this is a very poor connection. It's not even reaching MP, nor it is giving you the desired ductility. The second one is better because it is giving you strength, but it's still deficient on ductility. From the point of view of just resisting normal load, this is a good loads, it's a good connection. But from the point of view of being ductile, this is not a good connection because it will fail before it reaches the desired level of ductility. Then this is the other connection which does not reach its full strength but gives you ductile behavior. And the fourth one is the one which is desired, which has both strength as well as ductility. So if you are in this quadrant, they are good to go for lateral load resistance where you desire ductility. Just one statement I like to make here, not all connection need to be ductile. Some connection that you select need to be ductile and they need to be sitting in this quadrant and not in any of the 3 quadrants. So if you look at beam to column connections, you have these forces, axial forces in beams and columns, shear forces, and moments in beams and columns. The bending moment diagram typically looks like this. The shear force and types of deformation that you see as translation, rotation, extension. These are the deformation of this part of the, basically the joint deformation, bending, distortion. But if you have too much distortion or too much bending of the, or too much extension of the joint panel zone, you have situation like this where you have problems with the connection, where you have overstraining of complete joint penetration welds, local buckling, column kinking, local buckling of the web, and local buckling of the flange. So initially when they started research in the 1980s, they said if I'm able to deform this zone, this is the joint panel zone, it would dissipate a lot of energy. It was supposed to be a very good connection because it is dissipating the energy input by the earthquake and the structure is not collapsing. But later, now the philosophy is exactly opposite. We are saying that there cannot be any deformation in the joint panel zone and there cannot be any damage to the connection elements. So the desired behavior in lateral loads, this is the undeformed shape of the structure. This is the deformed shape of the structure for this. This is the way we design our structure. We apply horizontal loads. The code prescribed what this load should be. And based on this, if you look at one joint, then you have deformations of the joint as 3 parts. One is from the column, the second is from the beam, the third is from the joint panel zone. 3 deformation that contributes the total deformation at the joint, and that then adds on to the total drift of the building. You add it up at each floor. That will be a summation of all this, will give you the total drift at the topmost level of the structure. And this is one parameter that we always track to define the performance of the building or to evaluate the performance of the building. So system requirements, basically good structural system, configuration wise, all this have to be met with. Not to have a story mechanism. This basically, the yellow dots are the plastic hinges. Here the yellow dots are also plastic hinges. It's always better, or it is definitely better to have plastic hinges in the beam rather than in the column. If you look at this structure against this structure will collapse very easily because it's forming a collapse mechanism. And this will collapse only when the bottommost plastic hinges are formed at the base of the column. And this is capable of dissipating more energy than the other one. So this is a better connection. Then we have connection. Some parameters defined of the connection was special moment frames, ordinary moment frames. The rotation capacity should be 0.04 radians. That's a parameter like a drift of the building. This is another parameter that we track when we design connections. So panel zone deformation, this is what I was talking about, should be minimal, basically because having a lot of panel zone deformation basically will damage all the other elements that are making up the joint. So detailing of beam to column joints, basically existing approach is to have a plastic hinge based on the capacities of the beam, and this is the assumed stress strain curve of steel. You take this I-beam, define MP in terms of some factor, Fy and Zx, and then we say that this is a rectangular stress block. I don't know if you remember third year, fourth year engineering, we had a rectangular stress block which defines the plastic hinge capacity of the beam. But this is not the real behavior of steel. Like we saw in the earlier slide, this is the real behavior of steel. It does not remain flat. The bilinear behavior that is described in the code is not the behavior. This is the behavior. And there are times where structural steel, if you deform it sufficiently, will ride up on this curve, which will then give you higher stresses to be dealt with. So if you look at bending behavior, this is the elastic behavior, the first figure. This is strain below or up to yield strain. This is a straight line. When it goes into this part, yielding part, this is the shape of the stress strain curve, and this is the shape of the stress block when strain hardening occurs. So if you look at this part is coming directly superimposition of this, because the strains are always assumed to be linear distributed, which is a fact, has been observed during experimentation also. And based on this, if you look at this, we don't have this behavior. None of the codes or none of the labs that test steel don't give us this behavior. We don't know how much yield plateau length is. So what we do is we just join this part to we get this yield, we get the maximum stress that this can take, and you just join it with a straight line, and then based on that. So this is the code that we use for designing and detailing of our structures, IS 800. Most of you will be familiar with this. So when you look at this IS 800, it's supposed to, there's a chapter 12 in IS 800, which basically says that you have to design the connection for 1.2 times the beam plastic hinge capacity, and elastic deformation should be 0.04 without degradation below MP. So that's one thing which is unachievable in the code. This code is 2007, so almost 18, 19 years now. We are still working with that code. Many consultants have this difficulty, but we are not able to change that clause, and we are making do with the way the code is formulated. So assumptions is that the main assumption is Fy is only 1.2 times the minimum yield, characteristic yield strength. Strain hardening is not considered, like I showed you earlier. You just assume a bilinear stress strain curve. And elongation of steel, assume that elongation of steel will provide adequate ductility, irrespective of the force level that happen in the connection. So at this point in time, I'd like to define two terms here, just quickly. Ry and Ru, basically the red one, Fy star, is the actual value of Fy, the yield strength. Fu star is the actual value of ultimate strength of stress of steel. Fy is a characteristic value. Basically, Fe 250 steel will have 250 MPa, 350 will have 350 MPa. This is the one that is defined in the code. So these are the two ratios that we are going to look at. I will take you through a few slides. We did a small investigation on this to find out the values of this Fy and Fr. So what are the parameters that are required to define the stress strain curve? These are the parameters. All this, including the strain hardening slope, including the elastic slope. We know the elastic slope is 2 into 10 raised to 5 MPa is the initial stiffness of steel. But this is also required if you want to actually, if you're riding up here, what is the stress level and at what strain level it happens is required to calculate the actual forces that are going to happen in the middle. So elastic part, yielding part, and then the strain hardening part. These are the three parts that happen. So this is not available with us right now, and we have to make do with the kind of testing that we do in the field. So these are the two parameters. So this is the code which came out in 2023. Earthquake resistant design detailing of steel building. This is a parallel code to 13920 of concrete, which tells you how to do the detailing of structures, steel structures. So what we did before this code was developed, we took some samples. This is from IIT Kanpur. 5 samples were taken, and this was supposed to be Fe 250 steel. Ry value, this is the value of R, this is the definition of Ry, ranges from 1.24 to 1.7. If you remember, I said earthquake code Ry is in IS 800 is up to 1.2. But just 5 data points showed that it is much beyond 1.2. And if you use these values, this value of Ry, then the design of the connection will be highly underestimated. So looking at this 5 values, we collected, took us about 16 to 18 months to collect data. We collected 86 data points from various sources, material manufacturers, consultants, institutes, friends and clients and stuff like that. And we plotted this frequency against yield strength. This is a frequency distribution and this is for the ultimate strength, and this is the trend of mean yield strength to the size of the section. I'd like you to focus on this. Here, if you see it is supposed to be 250, the average is around 350. This is supposed to be 410. The average is around 480, 490 something. So much higher expected value, but much more than 1.2 in this range that we are expecting. Again defining, so this is that curve where we saw 250 is supposed to be 250. The mean is at 338. 95 percentile value is 1.6. 95 percentile value is the value above which most of the samples, or 95% are more than this value, is 396. I mean, only 5% of the samples will exceed 375. So if you see 375, only 5% of the samples out of 86 will exceed this value. So the mean Ry value, Ry is this definition here, is coming out to 1.5. Remember, 800 says that it should be 1.2. So these are the numbers that have been incorporated in the code. This is the new code that just came out 2023. For E250 steel, 1.4 Ry and Ru value of 1.2. We don't have data for this. This is just a consensus based number that has been agreed by the code writers. But somebody needs to get these values by doing a similar study. So if you look at the overstrength values, these are the values that we are looking at. 1.5, this is again for 250 steel, and Fu is 1.25. So these are the numbers that we have incorporated in the code. If you look at it here, 1.4 and 1.2. 1.4 because there is another factor that comes, and eventually Ry value that is to be used in design becomes 1.5. So just taking you through the design of moment resisting frame, how it is done. Basically, if you have a beam column connection and a plastic hinge forming away from the beam column joint, this is the length of the plastic hinge, LP, and for small rotation, if the rotation is theta and the radius of curvature is r, then these are the numbers that come in. So this is defined as rotation with respect to strain is a property of length of plastic hinge in the depth of the section. In the booklet that is given, the souvenir, this is detailed. I would like you to look at this. I wish I had a little more time. I could have gone in a little more detail with this. But so if you take any section, we took a flat section, W 24 by 94, this is the section, this is the dimensions of the section, and you apply whatever 23% strain, this is a stress block that develops. And based on that, if you take this and use these factors, Ry is 1.33, Ru is 1.18, 1.5 was for rolled section, this is for plates. So a section like this will not be available as a rolled section, so this will have to be made into built up section. So these are the numbers that are used. So if you look at MPR comes to 133, and MP is 1041. So these two numbers, if you compare 2000 against 1000, a factor of almost 2. So if you look at this, that the factor comes to 1.68. 1.6 is very far away from 1.2. I mean, too much of a variation. Expectation of code is too low. Similar thing we took. So if this is a very simple representation that comes out. Ry into Fy into Zx is this rectangular block. Our traditional MP calculation. You take Z of the section multiplied by the stress, you get the MP. And the other one is the elastic stress block. So if you add this up, this is where the MP comes to. So we took 25 of this, and we did for this 25 section listed here, we did the MF factor or the overstrength factor, which comes out to 1.86 for 1.13, and for I section, if I take these numbers, then it comes to 2. So the factor, again I'm reminding you, 1.2 is the number that we have to cross-reference this with. It's coming to 1.8. So our earlier code, IS 800 chapter 12, is highly inadequate based on the numbers that we have found. So this is the picture that we just saw. 1.5 is the Ry value, where this is the material gamma M that we multiplied with Ry. You get a number of 1.54 against what we have observed in the field is 1.5. Although this is a mean value, we we wanted to use the 95 percentile value, which is much higher. But then since code writing is a consensus based activity, we agreed on 1.5. Maybe next time we'll try to see if we can get a better number. So this is the code that I'm talking about, where we have this definition. These are the values that we are looking at, and field values of 95 percentile value, 1.65 is this. So it comes to 1.5 RY compared to 1.4, which is given in the code. These are the values. This I just showed you earlier. Same table I'm repeating, because this came out of understanding of 86 sections. So basic philosophy of earthquake resistant design is minor shaking, very little damage in structural elements, moderate shaking, some damage in the structural elements, strong shaking, lot of damage in the structural elements as well as the other elements, but no collapse. So this is the prime directive of our earthquake resistant design, and based on that we have these three types of connections. This is strong axis, strong column, strong beam. It's a weak axis, weak column, strong beam, and a box section. These are becoming fairly popular now, although we don't have any studies to design these, at least in the Indian context we don't have this. So if you look at a beam column connection, column beam reinforced here, these are the likely locations of the plastic hinge. You have to calculate these are the forces that will happen on the beam, the moment and the shear, the complementary shear that will happen because of this MPR, which we calculated earlier, is the maximum moment that can be developed in the beam when the plastic hinge forms there. So I'll just quickly go through an illustrative example of this. This is a simple frame. These are, it's a plan of a building, steel building. 2 frames in the X direction, 4 frames in the Y direction. And if you look at this, this is a 3D model of the building. It's a 4-story building, 5-story building with a mumty on top. So this one frame is here. You can see the frames here. This frame is on this face. Behind that there's one frame. On this face there's this frame. Inside there's one more frame, and same on the opposite side. So if you look at this, this was the final design that we got. These are the beams and the columns that we were designed. Notice that the E value, the Fy value of beam and Fy value of columns are different. We use a stronger material for column. Although if you look at this value, Zp and Zp for the column, they are different basically, because the depth of the beam is much larger than the depth of the column. But when you compare it with that, this of 1.2 times the MP value, the strong column weak beam definition, these two beams fit in that. So we determine the plastic hinge length, assuming the plastic hinge length of the connection to be about 0.5 times dB, and the length of the plastic hinge as again 0.5 dB, and L is the center to center from here to here, and this is just summation or reduction of L0, which is the length of the plastic hinge. It comes out to be 6.29, and using this we have a simple procedure. Assume or get the values of Ry and Ru. Now these are defined in the code. When we were working on this problem, this was done for rolled section. For rolled section, slightly lower value. So based on this, MP value comes to about 3000 kilonewton meter. And based on this, you calculate the shear demand, like I showed you earlier, comes to about 1000 kilonewton. And this is the connection that we designed for this, where you have a cover plate, 2 rib plates, top and bottom, twins. At the top, 4 at the bottom floor, and the complete penetration weld between all the ribs and the columns, column flange. So step 4 is to basically calculate the forces that will occur in the connection elements. Idea being to keep them elastic or keep the stress in them up to Fy value in the connection elements, not in the beam, in the connection elements. That will ensure that this is a reinforced connection, which then can be taken which will then push the plastic hinging into the column. These are the values that we got. Some assumptions were made in terms of what should be the width of the plate. The width of the plate should be slightly less than the width of the flange of the column, so that the welds can be deposited. These welds can be deposited. So those assumptions are listed. This example is again listed in the booklet that is being given to you. So step 4 is to calculate the shear capacity. Now we have designed the cover plate. These vertical plates have to be designed because there's an associated shear that comes with the column. So this is how the rib plates were designed. Von Mises was used, and this is one of the things. If you review IS 800, this is the way we calculate the thickness of the rib plates based on the shear criteria. So that is one of the parts that we were looking at. I went through this very fast. because I'm running out of time. This is the way we design moment resisting frame connections, and this is the way our code is asking us to design. No prescriptive moment connections are being proposed in the code. We don't want to have any prescriptive moment connection because it tends to be misused or wrongly used. Not misused, but it gives a false impression that your connections are going to perform the way they are supposed to perform, and eventually we don't want to get into a situation like Northridge because of the deficiency of the code. So quickly, buckling resistant braces. What is the buckling restraint? Basically means you restrain the buckling. So if you have a column or compression element, if you compress it from the sides, it will tend to buckle. We know this. But if you hold it in the middle, if you have a column 5 meters, you hold it in the middle, try to compress it, the 3 points will not move up and down, then the buckled shape would be like this. This is held, this is held, this is held. So these 3 points, if you are holding, this is how the buckling shape will be. So effective length is going to be half the effective length of a end held or end restrained brace. Now what happens if you have 3 or 4? You keep on increasing the this restraint, the lateral restraint to this. The 3, if you have 4 of them, it will bend like this because these dots are not moving because they are restrained. The fourth one will be like this. You keep on restraining it. Now imagine you restrain the complete thing, entire thing to be restrained. So when it is completely restrained, it will not buckle. It's not supposed to buckle. So that's what a buckling resistant brace is. Typically what happens is, I will not go through this, I had shown a derivation how you must be remembering P critical is equal to pi square EI by L square. This is the buckling load of a column. So this is a derivation which is not in the booklet. So if you do this, these are the solutions. Then you get this as a buckling load. P buckling load is a integer square times pi square EI by L square. L is the length of this is the length. So if you keep on increasing L, basically if you keep on increasing the number of restraints, this number will keep on going on. For 1, it's going to be pi square EI by L square. For 2, it's going to be 4 times pi square EI by. For 3, it's going to be 9 times. For 4, it's going to be 16 times. It's basically increasing in a quadratic fashion. So that's how the buckling load is defined. Now, what is the benefit of buckling resistant brace? Basically, in a nutshell, they don't buckle. They take a lot of load and they change the way the force are flowing down from the top of the building to the bottom of the building. In this case, the maximum force is going to be seen in these columns and the column at the behind. These two elements, these are representative basically of a moment frame. But if you have a buckling resisting brace, this is how it will be distributed. And the advantage being the axial load, axial compression and tension in the column is going to be much reduced because of the way you have modified the way the forces come down. So again, the concept of buckling, if you keep on increasing the restraints, then the axial load carrying capacity of the same material, if you are able to hold it together, is going to increase. This is basically the concept of confinement which we use in concrete also. This is the behavior of a brace. So if you see a buckling resistant brace consists of 3 items: the sleeve, which is the restrainer, and the core, which is yielding. Yielding has to be there because it has to dissipate the energy. One of the things that it does is it does not buckle, but it dissipates a lot of energy by yielding, as long as you're able to hold it together. So if you have a structure like this, which is a moment frame, will have a large drift. If you're able to restrain it in some kind of horizontals, it will have a lower drift. And if you have a better bracing system, then it will have very small drift. So our aim is to have small drift because we don't want to deflect the building too much. These are the configuration of buckling resistant braces. The outside gray one and the black line basically is the restrainer and the filled up material, and the red line is basically the yielding material, that is this, which basically is the buckling part, or which is the yielding core, which allows you to dissipate energy. These are the components: restrainer, core and filler, which basically brings you this. And the debonding material. Basically, you cannot have a buckling resistant brace which is going to bond with the filler material, then it will start behaving like a composite and it will create a global buckling. And connection between the structures. So basically, wherever the buckling race, these are the parts where you have to connect it to the top corner and the bottom corner of a frame. Those are also important. And if you see, the more the axial force capacity increase, the more amount of force has to be transferred to those joints. So that is how buckling resistant brace, you have to get a better idea of what is the yield capacity of that material and design it for that. The connections have to be designed for that. This is one of the buildings. In the morning we saw, this is another hanging building. This is a building hanging from top actually. There's a core in the middle. And these are the buckling resistant braces that are installed. You can see this, these are not the columns basically. These are just framing columns to hold the outside facade. This is another hanging building. This is the LA Court building, Clark Construction Company of the US. They installed this. They did the core first and they suspended it from the top. And they didn't use the lifting mechanism, but this was done in a similar fashion. The principle is same. You create a structure and hang it from the top. But this hanging was achieved by this massive braces. This is the top header truss that we were looking at in the morning. Similar trusses formed by buckling resistant braces. This is another picture of that. Another buckling resistant brace picture. I'll just take 2 more minutes. Advantages, disadvantages. All braces, all systems have advantages. Advantages is all this. Good load path, high energy dissipation, effective in retrofitting. It's a very good solution for retrofitting. It's localized damage. Only the brace gets damaged. You can take it out and replace it with a new brace. Disadvantages, Indian standards are not available. We don't have any Indian standards telling us how to design them. Needs special material. It has to be ductile. It has to be, it has to damage and dissipate the energy. With no strain hardening. If it strain hardens, then the capacity suddenly goes up. We need to design the connections properly, and height restrictions on the buildings are there, because if you have 70-80 story building, then the global mechanism takes precedence over the local buckling, and they need to be replaced after a major earthquake. Performance problems, mortar and core act as composite. If the core, the yielding core and the mortar, they become together, then behavior is not as expected, and it can have a catastrophic failure, because the whole thing will act like a single column and have a global failure. So modes of failure, if you look at this is how the load transfer happens. So if you look at closely, when the inside is basically doing up and down during an earthquake, then because of the extended strain here and the fatigue properties of the earthquake, this will start cracking and the material can deteriorate. So this has to be taken into account. Local buckling of failure of the restrainer. Restrainer is the outside cover, including the filler mortar and the tube outside. The tube can buckle. If this is pushing it out, the tube can buckle. So tube has to be designed, or it can be fractured because of the constant earthquake impact load. Connection failure, basically whatever connection you're providing, that needs to be designed adequately so that no fractures or no yielding of the connection happens. If the connection yields, then the buckling resistant brace is not going to perform as desired. And one of the major problems that has been observed is the mortar which is put inside. If it is bonding with the yielding core, then they start behaving like a single unit, and then the global, the failure will be as a global buckling mode and not as a local buckling mode. This will disrupt the load path which you have assumed and will lead to catastrophic failure. Result also in large drift. This is the global failure mode. If basically it becomes a single unit, it will buckle as a single large column and not do the zigzag thing that we saw. I think that's all I have.
I've seen some in the San Francisco and all that regions, they were inserting some special movement resisting frames in the ordinary buildings for the seismic upgradation point of view. Is it for the controlling of the drift or the controlling of the forces?
So, inserting moment resisting frame, I'm not aware of. You may be talking about inserting a base isolation layer at the bottom.
No, sir. It is a special momentum resisting frame they were designing.
In
the existing building, in one bay they were inserting.
I don't think that is there, but I'm not aware of this. Maybe
yes, I have seen, sir.
Yeah, okay.
Second question, quick questions.
Yes.
Like in the E-tabs, we are modeling using the fiber hinges for the RCC structures for the plastic hinge modeling. Do you have any modeling in the steel frame structures for modeling of the
in which structures?
Steel structures for modeling of the plastic hinges.
E-tabs does, STAT does, MIDAS does. Any software you pick up, all of them do the same thing. There's nothing special about E-tabs or STAT. All of them do the same thing. Just the way it presents it and that's the way you model it is little different. The graphical user interface is different. But all softwares that our codes or the analysis method do are stiffness methods, elastic analysis. If you have to go to nonlinear analysis, then that's a different ballgame. We don't have softwares for that. Some specialized softwares are offering nonlinear behavior, but the behavior is defined based on how the moment rotation will happen.
Moment curvature relationship.
Yeah, moment rotation which is there, that you have to define properly. Only then it will represent your structure. But as long as the elastic analysis is done, all softwares are same. ETAB, STAD, SAP, what else do you use? Pagoda, the Aigoji Pagoda in Japan, it was built in 1874, 5-story wooden structure. Kyoto is a region in Japan which sees a lot of seismic activity. This is a 5-story structure completely built in wood, no damage. Till today, it must have seen maybe thousands of earthquakes of magnitude more than 4. If you look at this images, if you see, okay, they go back, insert some prop and hammer it back into position. It's a kind of moment resisting frame, but it is slip. Basically, there's a cup like this and there's a member sitting in the cup. When there's an earthquake, it allows it to slip. So if it is too much of a slip, they just insert a prop and they hammer it back into place. So very innovative, structure, but those are the kinds of design maybe we should be thinking of.